Okay, YouTube, in this particular video on solving exponential and logarithmic equations, we're going to look at some situations that are just basically modeled by exponential and logarithmic models and how we could use those models to solve for unknown values in a given instance. So let's take a look at this first here example. We say our first applied example provides a mathematical perspective on the old slogan, alcohol and driving don't mix. So we say in California, there were, 38% of fatal traffic crashes involve drinking drivers. It is illegal to drive with a blood alcohol concentration of 0.08 or higher. And this is actually a pretty prevalent number, ubiquitous. You find it in a lot of different states, but it says at these levels, drivers may be arrested and charged with driving under the influence. So looking at our model here, we can see that we have some exponential model that's going to relate, it seems, R and X. And let's talk about what these are. It says medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. And this risk is modeled by this model here. So we say X is the blood alcohol concentration. So when you put in a blood alcohol concentration, what happens is we get an R, which is given as a percent, and that is the risk of having a car accident. So with any model, I always like to label these things here. We say our risk, and risk is given as a percentage. And that's if we know our, I'm going to write blood alcohol concentration in your blood, okay? But looking at our graph over here, you can actually see this as the blood alcohol concentration goes up from 0.05 to 0.25, yikes, you can see this risk factor just climbing really, really sharply here. So the question we want to answer is this: what blood alcohol concentration corresponds to a 17% risk of a car accident, and how is it shown on the graph? So when we talk about 17% risk, the interesting thing here is I've either given you an X or a Y, or in this case, an X or an R. And because this 17% represents a risk, what we're actually going to do is go plug it into our model for our R. So what we end up with is 6e to the, looks like the 12.77x, which is our blood alcohol concentration. And we'll just put a 17 here. It's just that now we're very well equipped to solve equations of this nature. So first of all, we'll get the exponential thing by itself. We get e to the 12.77x power, and that's equal to 17.6. Now I'm going to encourage you to leave it this way. But the idea is now that we have the exponential base by itself, let's go ahead and do this. We'll just take the ln of both sides. We'll do the inverse of e to the power of. We'll do the log base e of both sides. And so on the left side, I'm going to write my work over here. Now we say the ln of 17, oops, let me get that 17 back up there again, 17/6 is equal to just 12.77x. And so now, dividing by 12.77, we can actually get a decimal value for this and say, well, then your blood alcohol concentration, I might as well write approximately, get my calculator out here. We need now the ln of 17 divided by 6, all of that over divided by 12.77. So what we end up with is about a 0.081-ish or a 0.082-ish, so 0.082-ish, okay? And so we'd say, how is this shown on the graph? Well, what I could say is that when you're looking at the risk here, I would say that looking at the scale, I guess if this is 20 and this is 40, we got 1, 2, 3, 4. It must be going by fives. So this is 5, 10, 15, 17. If we were to go out 17% risk here and come down and hit the graph, you could see that this 0.082 is what we've just kind of discovered here. So using the same formula that we've got in this example here, what blood alcohol concentration corresponds to a 7% risk of a car accident? We'd say 7% risk, that's going to be down here. So it's kind of off the model, but I want to know, when you plug in a 7% into your model for R, what do you get for your X? I'm going to leave that to the viewer as an exercise and move on to these last two examples, one involving another exponential equation and the last one involving a logarithmic. So let's look at a pretty common example here. We say, how long to the nearest tenth of a year? So we're finding a year here. Will it take for $1,000 to grow at $3,600 at 8% annual interest compounded quarterly? So what we're going to do is we're going to use our model for n compoundings per year, which is the amount equals p times 1 plus r over n to the nt, where our amount, a, here, would be equal to what we started with times this 1 plus rate over n, where n is the number of times it compounds per year, and then t is our time. So what we're really looking for here is the how long. And you can see with our model what we're really looking for is this. So we must know everything else. So let's go ahead and take a look at this. We say that this 1,000 represents our initial investment, and this 3,600 represents the amount we wanted to get to. Our 8% is our R, And compounded quarterly means that our n value is going to be 4. So filling all of this in, what we end up with is 3,600 is our amount, equals our principal amount, which was 1,000, and then we have times 1 plus the rate. Now the rate, 8%, needs to be written as a decimal all over n, and this is all to the nt. So you can see how in all of this mess we're going to have to get to this t, which means if you're listening to my advice, we need to isolate the base of this exponential expression first. So the first thing we're going to do is we're going to divide both sides here by 1,000. And so dividing by 1,000, we end up with this here. We would get 3.6 on the left. On the right side, we just get, now, this 1 plus 0.08 divided by 4, that's really, if you put it into a calculator, 1.02, and this is to the 4t. But the idea here is this. Now we're going to take the log of both sides. And so my suggestion is that we take the log base 1.02 of both sides. Log base 1.02 of 3.6 is the same thing as log base 1.02 of 1.02 to the 4t. So with these canceling out, we get log base 1.02 of 3.6 equaling 4t. But to solve for this time, what we'll do is we'll just divide by 4. So our time is going to be equal to this here. What we're going to need to do is rewrite this top portion as a change of base situation. So I'm going to use ln. But the ln of 3.6 over the ln of 1.02 would be our change of base that tells us this on a calculator. And then we're going to divide that by 4 to get our time. So with our calculators here, let's go ahead and do this. We say, clear, ln of 3.6, that divided by the ln 1.02, enter, and then we're going to divide that by 4, enter. We could say that it's going to take 16.1 years, so about 16.1 years. Okay, so in this last example here, it says the percentage of adult height attained by a girl who is X years old can be modeled by this, where X is the girl's age from 5 to 15. So we'd say that this right here, if we're going to label this, and our model is age from 5 to 15, and f of x represents the percentage of her adult height. So we say the percent of the adult height that she'll have at that particular age. So it says what age has the girl attained 97% of her adult height? So the idea here is that when given this 97%, we're given a y value. And again, what we're going to do is we're just going to put that in for our f of x value or our y value here. And we get left with this here that we need to go solve for an x for. And x is right here. So the idea is that we're going to have to get this log by itself first, starting by subtracting 62 from both sides. We got to get the log by itself. So 62 from 97 is going to give us a 35, and that's equal to 35 log x minus 4. So what we're going to do now is this. We're going to divide both sides by the 35, and we get left with this. 1 equals log of x minus 4. So now that this logs by itself, what we're going to do is really just rewrite this in exponential form. So we end up with this statement. We say 10 to the first power equals x minus 4. And this is awesome because we can just add now 4 to both sides. And what we end up with is x equals 14, which you should certainly check. But when we say 14, what does this 14 represent in this application situation? That was an x value, so we'd say 14 what? 14 years old. And at 14 years old, we can speculate that a girl would reach 97% of her adult height. Cheers.